In this presentation, we're going to add a breadth-first search to our matrix, to our graph that's been implemented as an adjacency matrix. In a previous presentation, we looked at the breadth-first search algorithm and traced through it to see how it works. And so now I think we're ready to actually try to add the code, the capability to our adjacency matrix graph to perform a breadth-first search and try to find a path for us. As you recall, our current graph code has a list of nodes implemented as a vector of string, and the edges are in an adjacency matrix that's a dynamic two-dimensional array of integers. So it's a vector of integer. What we'd like to be able to do is, given a starting node and given an ending node, can we find a path? And if you recall, the breadth-first search does not necessarily find the shortest or most optimal path, but it will find a path if one exists. So let's take a look at how we might do that. We already looked at the breadth-first search algorithm we used, and we traced through it, and we used the one that was in Wikipedia, and we had to make a couple of changes to the algorithm. The first one is that we don't have the capability of labeling a vertex or a node as discovered. Our nodes are just strings. So instead of doing that, we created a discovered list that we can search in and ask yes or no, has this node already been visited or discovered? And then the second one is we don't have the capability of labeling a node as having a parent. So there's no way of, again, our nodes are just strings, so we can't say that we got to this particular node by coming from some parent node. There's no way to do that easily within a string. So we're going to use a hash table or a dictionary or in C++ an unordered map to mark these parent-child relationships. And then of course we need a queue capability. So let's see how we might add this in here. We know we're going to need a queue and an unordered map. And we already have a vector that we could use as our discovered list. So now what we might do is to write a function in our graph class to do a breadth-first search. And we're going to do this in at least two steps. The first step is that we're going to just do a breadth-first traversal and not really be concerned with searching for a particular path. We're just going to traverse the entire graph and print out all the nodes as we visit them. And then we'll go back and modify it to do an actual search for a path from a beginning node to an end node. So one of the first things we'll do is to ask the question, is the beginning node even in the graph? And maybe we need to ask if both the beginning nodes and the ending node are in the graph. And we do this with the find function that we've done in the past. So we ask the question, if in the range from node list begin to node list end, does the beginning node, is it found? And if it's not found, it'll return this the end of the node list. So this effectively asks the question, does the beginning node exist in the graph? And if it does, we'll set up some variables that we'll use. The first is the queue that we need for the breadth first search. So we're going to make a queue a string, call it node queue, and then we're going to make our discovered label, our discovered list, I call it a visited list. So it's a list of nodes that we've already visited, so we don't make sure we don't backtrack. And then we need to mark nodes as having a parent or not. So as we visit a node, we need to know how we got to that node. What was the parent in the path, or how did we get there? So we will do this with an unordered map. So this is kind of like our trail of breadcrumbs. How did we get to this particular node? Where did we come from to get to this node? And that'll help us find a path a little bit later on. So this sets up not only the queue, but also a couple of other data structures that we need to implement this algorithm. So now we need to label we can label the starting node as discovered. So our starting node is begin node. So to label that it's been discovered or visited, we just push it into the visited list. And then later on, if we want to know whether a node has been visited or discovered, we can just do a search with a find like this. The next step that we'll do is we'll initialize the queue, in queue the starting node. So we're just going to initialize, start off the queue with the beginning node. And then we'll set up this loop while the queue is not empty. So while the node queue is not empty, we want to create the current node V. I'll call it current node. I prefer a more meaningful variable name, so I'm going to call V the current node equals and we don't have a DQ in C++'s standard template library queue, so instead we use a combination of front, and that just copies the value of the front of the queue into the current node, and then we use pop to remove it. So this combination of front and pop is the equivalent of the DQ that's here. So now the next question here is we're going to ask if V is not the goal. So our goal is end node, and currently we're not really looking for a path. We'll go ahead and write this in here. So if V is not the goal, so that means if the current node is not equal to the end node, do something. If it is the goal, then we're really finished with the search, and we'll stop with the search. For now, we're not really looking for a path, so I'm going to comment this out and just put a true here. And this will allow us to traverse the entire graph, and then we'll come back here and modify it to actually search for a path. So we're not really worried about whether we've found the goal just yet. We want to traverse the entire graph. So now the next part gets a little bit trickier, where we want to loop through all the nodes that are adjacent to the current node. So this gets a little bit tricky. Before we do that, let's print out the current node. After we remove it from the queue, let's go ahead and print it out. And it's just a string, so no problem printing that out. And now we want to find all the paths that come out of this current node, or all the nodes that are adjacent. How can we do that? If you recall, our graph is stored in an adjacency matrix. So and we've done it in a way that the rows, we can consider the rows as the from nodes, and then the column as the to nodes. So if we do a search in the node list for the current node, it will give us the index of the row for that particular node. So remember that our node list maintains the list of nodes in the same order that the rows and columns are in. So if we do a search in our graph, in our node list, for the current node, it can tell us, we can find what the offset of that node, say C is from the beginning, and that would be 1, 2 offset. So that would give us the index of this row. And then we could iterate through this row, and for every non-zero value, that is a path or an adjacent node that's coming out of this current node. And as you recall, we have the capability of searching for a node we can search for a node, and it returns an iterator to the vector that's our node list. And if we take that iterator and subtract from it the beginning of the node list, that will give us an index into the node list, which will be the same as the index into the adjacency matrix. So that code will look something like this. So we search for the current node in our graph, and that returns an iterator. And if we subtract from that iterator the beginning of the node list, that gives us the index of that current node in the node list. And that will coincide with the row index in the adjacency matrix. So then we can step along the column, each column of that row, and for every non-zero value, that gives us a path or an edge coming out of the current node. And that's exactly what the algorithm is looking for. So then the next step in the algorithm is to loop through every column on the row of the adjacency matrix, the current node index row of the adjacency matrix. And if that entry is non-zero, or if it's a 1, then that means we found a path coming out of the current node. So that implements this for loop in our algorithm for all the edges that are coming out of V, which I call the current node. So now the next step is to ask this if statement. If W is not labeled as discovered, and the way I word it is, have we already visited W or the adjacent node? So let's get the adjacent node first. The adjacent node, or W, is going to be equal to our node list subcolumn. So as we step through the row of the adjacency list, the adjacency matrix, and when that column index gives us a non-zero value, we know that we found an adjacent node. So there's a path from C to B. There's a path from C to B. So then we can get the adjacent node B as simply the column that we used, 0, 1, looked up into the node list. So now, according to the algorithm, we want to ask the question if W, or in my case, the adjacent node, is not labeled as discovered. And I like to translate that as, have we already visited this adjacent node? As if we have, we don't want to backtrack. And so that involves us searching in this visited list. So we want to ask the question, and the way we do that is we can simply use the standard find algorithm, and we can search from the visited list begin to the visited list end, and we want to search for this adjacent node. And if we find it, it'll return the visited list end. And we want to know if we don't find it. So it'll be equal to visited list end. So this essentially says, or asks, is the adjacent node not in the visited list? And if it's not, then we want to go ahead and visit it or mark it as discovered. So this is our C++ translation of if W is not labeled as discovered. So the next thing we want to do is label it discovered, which means put it in the visited list. So then we push back, and then the next step is to set this adjacent node's parent as the current node. So this means that in our parent map, we want to set the adjacent node's parent as the current node. So this is a hash table or a hash map or a dictionary we're setting the parent of the adjacent node equal to the current node. And then step 13 here, we want to enqueue this adjacent node. So we're pushing the adjacent node into the node queue, and we can continue our search from this adjacent node. So this is our algorithm for traversing, and at each step in the traversal, every time we process a new current node, we'll be printing it out. So if we run this, we should see that we're traversing in a breadth first order, meaning that we process the current node, then we process all nodes that are 1 hop away, then we process all nodes that are 2 hops away, and so on. That's the order for a breadth first search. And so if we call this in our graph in main, we should see the nodes being processed in a particular order. Now we do need to specify the start and end node, even though we're not really using the end node right now. We're not looking for a path, but we do need to specify where we're beginning. So let's take a look at our graph. This is the graph that we've been using. And let's just say we start at F and see what we get. Maybe we're going to search from F, a path from F to A. We're not really using the A right now, but let's see if this will compile and run. So here is the results. This is our adjacency matrix that we printed out before, and now this is the breadth first traversal. So the first step was to go from F to D, so that's 1 hop away, and then we went from D to A, so that's 2 hops away, and then we also went to E, which is 2 hops away from F. Then the next one we did was B, which, whether you go from A to B or from E to B, is 3 hops away from F. And then the last one we did was C, which is 1, 2, 3 hops away from F. And you could also get to C with 1, 2, 3, 4 hops, but we don't get that far in the breadth first search because C has already been visited. We've marked it as visited, so we don't get that far. So this is traversing the entire graph in a breadth first fashion, but it doesn't really give us a path. So this is where we need to look in the parent map to find a path. So let's see if we can print out the parent map before this function is done. So when this queue is empty, what are the contents of the parent map? So that is this. So I'm using control right brace to find the matching brace for this while statement. So that's the matching brace, and here I want to just print the parent map. So I can say for do a range-based for loop in our node list, and then print out what is the parent of each node in the node list. So So let's see what happens when we run this. What do we get for the parent map? So this is what we got on the output of the parent map. So notice that we started our search from F. So we were searching from F to A. So we started our search from F. So F doesn't have a parent. And then E's parent was D. So from F, we were able to get to E by passing through D, and that makes sense. D's parent was F, and that makes sense. C's parent was A. So we were able to get from C through A. So we went from F to D to A to C. That makes sense. That's 1, 2, 3 hops. So that makes sense. And then we were able to get to A from D. A's parent was D. That makes sense. And then B's parent was also A. So just like how we got to C, we were able to get to B by going from F to D to A to B. So B's parent was A. So this makes sense in our map. So if we were to reverse this process and say, okay, we're looking for A, and we got to A by going through B, and then we got to sorry, we need to look at the other way. We got to A by going through D. So if we're trying to find a path from F to A, we got to A by going through D, and then we got to D by coming from F. So our path then in reverse is F to D to A. So you can kind of see the path in reverse if you start from the end node that we're looking for. But it might be nice to be able to store this. And because it's in reverse, if you recall, we can reverse a set of values by using a stack. So if we put values into the stack and then pop them off, they'll be in reverse. And that's kind of what we're trying to do by looking at this parent map. So to actually get us a path, we'll modify the breadth first search to pass in, or to have it return us a stack of pairs of nodes. So we'll create a stack of a pair of nodes which are just strings. So we'll come up here and include stack, and then we can have the breadth first search to us return to us a stack of pairs of strings. And then we can set that up as the value that we're going to return. And return it at the end when we're done. Now we need to modify the code here so that here we search the entire graph, and we may not need to if we find the target value or our goal early. So we can take out this true. Instead of traversing through the entire graph, we can say, let's stop the search if, let's don't continue searching if the current node equals the end node if we found our goal. And then, instead of printing out the parent map, let's convert the parent map to a path stack. And we only want to do this only if a path exists. So it may be possible that there's the path from a particular node to a particular node doesn't exist. That's a possibility in a graph. So we want to maybe check for that. So what we'll do is that the unordered map has a find function, and we will search the parent map for the end node. So this looks in the keys of the parent map for the end node. So it's looking in the left values here for the end node, our goal. If our goal isn't there, that means we didn't find a path to it. So we only want to do this if the path exists. And if we did find the goal or the end node as one of the keys of the parent map, then we can loop from the end node back to the starting node in our parent map, and for each step of that loop push in the path from one node to the other. So we're going to start with the end node, say A, and say we got 2A from D. So then in our path stack we're going to push in D to A, the parent to the child. And then we're going to take that parent and look to see how did we get to D. Well, D's parent was F, so we're going to push in that parent to child as F to D in our path stack. And then when we take the values out of when you take those pairs of values out of the path stack, they'll be in reverse order because they've been put on a stack, and then we'll get the path F to D and D to A. So we'll set up a loop here. And as long as the current node is not equal to the beginning node, we want to keep going through the parent map. And we're going to get the parent map, or the parent node, as the parent of the current node. And then we're going to push in a value onto the path stack. And the way we'll do this is we're going to construct a path or an edge as a pair of string node names. And it's going to be a little bit, seems like it might be a little bit reversed, but we're coming from the parent node and going to the current node. And then after we've done that, we're going to make the current node, update the loop by making the current node equal to the parent node. Okay, so we're going to start the loop by setting the current node equal to the end node, and let's say that that's A. And we're going to check to make sure first that that end node A is in the parent map. We can find it, and we can. So that means we've got a path. And then set the current node equal to that end node A, and then while it's not equal to the beginning node, which is F, we're going to get the parent node of the current node. So A's parent node is D, and then we're going to push a path into the path stack from the parent node to the current node. So we're actually going to push in D to A into the path stack. And then we're going to set the current node equal to the parent node, which is D, and we go back around. So D is not the beginning node F, so then we're going to say that the parent node of D is whatever the parent map of D, which is F. So then we're going to push in a path from the parent node F to D. So now the stack has F to D on top and then D to A on the bottom, and when we remove those values from the stack in that order, we're going to get a path from F to D and D to A. So this fills in, converts the parent map into what I call a path stack that we can remove from and actually see the path. So then in main, when we do the breadth first search, we're going to get back a stack of pairs of strings and then we can say while the path stack, we can print it out. So we do a breadth first search from the start node to the end node and store the result in that path stack. And then we can print out the path. While the path stack is not empty, that should be not empty. So as long as the path stack is not empty, we want to get a path or an edge which is going to be on the top of the path stack, and then we want to remove it. So in the standard template library, the pop operation removes, but it doesn't return it back. So actually to do a classic data structure stack pop operation in C++ SDL, we have to copy the top of the stack into a variable and then pop the top value off the stack. Now we want to print out the path or the edge, and it's going to be the edge first and the edge second. So we've got variables now for the start and the end node. We do a breadth first search from the start node to the end node and get back a stack of edges or paths. And then we set up a little prompt, maybe an extra endl here. And then for every path or edge in the path stack, we pop it off and print out the first node and the second node, which is where it's coming from and where it's going to. So if we did this right, not only do we get the traversal of all the nodes in the graph, but we also get a path that we're looking for. So a path from F to A is F to D and D to A, F to D and D to A. Let's try a different one. Let's see if we can go from F to C. So again, we've got the traversal, but we have a path from F to C as F to D, and then D to A, and then A to C. So we found a path from the beginning node to the end node using a breadth first search in our graph. So this is a nice implementation of a breadth first search looking for a path in a graph. The other common search algorithm called depth first search works very similar, but instead of looking at nodes that are 1 hop away, 2 hops away, 3 hops away, it actually goes as far as it can first and then comes back and backtracks. And the code, the algorithm is very similar, but instead of using a queue for the breadth first search, it uses a stack, and there's 1 or 2 other minor changes. You can find that algorithm online fairly easily. So let me know if you have any questions about this graph traversal and graph searching.